Okay, gang. Well, so I'm going to try something different this time. I'm re-recording my Stellar Evolution, The Life and Death of a Star. This time I'm using voice narration, and then I'll try and publish that as a YouTube, and then maybe that'll be a little easier for you guys in the class to watch this at a time that's convenient for you. So I'm just going to go ahead and then we'll arrange later by email exactly how you can contact me and talk to me about questions and so forth if you have them. Okay, so we're doing this week the evolution of stars, the life and death of a star. This is a little summary of what we're going to talk about. We're going to look at how low mass stars evolve, high mass stars evolve, and then something I'm going to do that's a little different than the textbook. We'll talk about how low mass stars are really more properly divided into low and medium mass stars. Okay, so the first thing is that stars are always born in star clusters. I think we talked about that when we did our lecture on star formation. Why star clusters? Because we need enough mass to get enough gravity to make stars. You're just not going to have the conditions be right for the formation of one single star out in the middle of nowhere in our galaxy. The gas densities are too low, and the environment with other stars shining on it is not right. So what we need for gravity is we need low temperatures, so the gas doesn't want to just wander away. Remember what low temperature means. It means slow velocity for the individual particles. And since gravity is very weak in these low-density environments, then you need that kind of help. So by low temperatures, we mean something like 30 degrees Kelvin above absolute zero. Way, way colder than what you might think of as cold here on Earth. We also require dust, so dust helps to be a little landing pad for atoms to land on, like hydrogen and carbon and oxygen, and then after they land on the dust, then the dust can help those atoms come together and become molecules. They may drift off again, and then collisions between molecules actually excite the internal motions of the molecule, which then de-excite, giving off infrared photons. And in a very low density gas like this, those infrared photons are very likely to just escape. So the net result is they're a coolant. They take away the velocity energy of the gas, and therefore helps gravity to pull things all together. So there's an open star cluster, a pretty rich one. I think this one is M11, the wild duck cluster. Notice how many of the stars are blue. That's main sequence stars. They're just beginning their hydrogen burning. I see a few red stars here. Those might be early red giants. They look a little too bright to be red dwarfs. Red dwarfs are the lowest luminosity stars, and they're quite a bit less luminous than main sequence stars that are white or bluish white. So I'm guessing these are actually high mass stars that have already evolved off. That's the story that we're going to fill in as we go along. So these star clusters inherit the internal motions of the gas, and therefore you should think of them not as a static thing, which they may look like to you during your whole life. I doubt that you'll see any change in the positions of these stars. However, if you age over thousands of years, you'll see that they wander, and if you speed them up to a time that's more appropriate for the evolution of star clusters, you'll see that they actually, it's like a kind of a crazy square dance, a bit of a random crazy square dance, and so the stars pick up energy. Some of them will actually evaporate at the expense of others who get in closer. And eventually, just about all the stars will evaporate, but you may make some tight binaries in the process of losing energy. So the clusters get wider and more widely diffuse, and then eventually we don't call them a star cluster, we would call them an association. So prominent associations in the sky is the Alpha Persei association, made up of the bright stars near Alpha Persei. And then the most famous one would be the Big Dipper. So the Big Dipper stars are actually all members of a single star cluster, about 75 light years away. And the interesting thing about that cluster is that association, as it expands, the boundary of it is already past the location of the sun right here. So we can identify, using velocity measurements, we can identify members of that old cluster, which is now represented by a denser core. Doesn't look all that dense to us, but it's very, very close, obviously. Very dense core of stars that's the Big Dipper in the sky. So that's kind of cool. The Big Dipper and Coma Berenices are the two examples of constellations in the sky, which are not just constellation figures, but they're actually physically associated stars. So they're members of a star cluster. Okay, so this shows how the mass of a star and a planet is related to its diameter. So what this figure is showing is that if we add mass to a planet like Jupiter, what will happen is the gravity will get stronger and the planet will actually get smaller. So it will move along this track, getting smaller but yet more massive, until finally, at a point right about here, at 0.08 solar masses, you now have made the interior of the star hot enough, roughly 10 million degrees, that now hydrogen fusion will begin. And then that new energy from the core will add heat to the interior and puff out the star. And now if you add more mass, the core will burn energy faster. It will puff the star out more, and so the diameter of the star will now grow, kind of as you might more nearly expect. But initially, you can see that what happens is the mass of the object goes up while the density goes up as well, and so the object actually gets smaller. So there's low, medium, and high mass stars. So when I learned my stellar evolution, it was from Lawrence Aller, who was kind of widely regarded as the dean of stellar evolutionary theory and observation back in the 20th century. So I had the privilege of being with him during his later years at UCLA. And he was an advocate of dividing the stars into not 2 mass groupings, but 3. And I think that makes perfect sense, so that's what I'm going to do. I tried arguing that to our authors of our textbook, but Bennett et al., and they decided they were just going to stick with what they got. So anyway, I think that we need 3 mass groupings. Let's talk about the evolution of these 3 mass groupings separately. So low mass stars can only burn hydrogen to helium. That's all they can do. When they've converted their mass into helium, they cannot get their cores hot enough to do any further nuclear burnings. Medium mass stars can burn hydrogen to helium, and then they can actually burn helium to make carbon, and perhaps beyond that, up to but not including iron. High mass stars, the dividing line for high mass stars is stars that are about 8 solar masses or higher, and these can fuse elements up to iron. Then when that star gets to the end of its fusion, it has a very dramatic end. It blows up as a supernova. So let's go through all that. Okay, so stars burn through their hydrogen. They evolve off the main sequence to become red giants, and then they die in various ways. Higher mass stars evolve fast. They make lots of different chemical elements as they evolve. The more mass they have, the more different chemical elements they can fuse. The lower mass stars evolve slowly. They make only helium, maybe carbon. And again, if they're medium mass stars, then they may make carbon and then up to oxygen perhaps, and a few others beyond. So stars age at very different rates depending on their mass. The more mass, the faster they evolve. Okay, so low mass stars. Again, when I use low mass stars, I'm talking about stars that only burn hydrogen into helium. So they burn hydrogen to helium. Now the helium is a denser atom than is hydrogen. So as the hydrogen turns to helium, then the core gets more dense. As it gets more dense, it's falling together under gravity. The star is tapping the second of its two inherited energy tanks, we can think of it. So a star starts out with two fuel sources. One of them is hydrogen fusion, really nuclear fusion in general, let's say. And the other is the gravitational potential energy that they inherited just from the fact that the matter is spread out initially into this interstellar cloud. Letting it fall together under gravity will release that gravitational potential energy and can heat the star. So during the star's life, it taps both of these energy sources at different rates at different times. So the helium can't burn for a low mass star. It can't get the helium hot enough. And the electrons in the center will get close enough together at a certain point that they can't get any closer. So the star can't do any more nuclear burning. It's out of nuclear fuel. And it also can't tap gravitational potential energy because the star is held up now by so-called electron degeneracy pressure. The electrons, let's just say for the moment, they refuse to get squeezed any tighter, and I'll flesh that out a little bit more later when we get to the end state of medium mass stars, when it's a little more relevant. But at that point, the outer envelope is not going to be held up because the luminosity generation is turning off. And so the outer envelope is going to move back down, and the star will contract. And as it contracts, then the outer envelope is now tapping gravitational potential energy, and so the surface of the star will heat up. And so what the star will do on the HR diagram is it will move down and to the left. Remember, to the left is hotter temperatures, and down is lower luminosities. And it will eventually come all the way over and join the white dwarfs. Those are the dead stars. Dead stars are stars that are still hot. They may be very hot, in fact, but they're no longer generating any new energy, and they're merely just cooling off. So we'll talk about white dwarfs in a little more detail later. Okay, so we talk about medium mass stars. Medium mass stars will burn hydrogen to helium. Now you've got hydrogen and helium bouncing around the core. What can you make from these? Well, you can combine hydrogen and helium and make lithium-5. So that's shown right here. But lithium-5 is extremely unstable. There's too many protons, not enough neutrons for binding, and it'll immediately fall apart. So the star's not going to gain by that. It is not going to go. You could also try combining the two heliums, and then you'd make beryllium-8. But beryllium-8 is also unstable. It's not a low energy configuration, and it will immediately fall apart as well, back into two heliums. So the only solution is for the density and the temperature to rise not a little higher, but a lot higher. Not to the 18 million degrees optimum for hydrogen burning, but to 180 million Kelvin. And at that point, you can have the two heliums combined to make beryllium-8, and the beryllium-8 lasts just barely long enough that it will be hit by yet another helium-4. And so now you've got three heliums running into each other, and that will stick because that's carbon-12. So that's 4 nucleons each. That's 2 protons, 2 neutrons, times 3. That's ordinary carbon-12. 6 protons, 6 neutrons. It's very stable, and it releases a decent amount of energy, and so this is what powers the star now as it has gotten to that point. Medium mass stars will get to this point. I'm only going to just very briefly mention this. So there are several different ways to produce helium from hydrogen. Proton-proton chain, and there's a couple of variants. depending on whether you make deuterium, like at what point you make deuterium. I'm not going to ask you to remember those details, so I'm not going to go over them. But that's one way, and that's the way that lighter mass stars, like the Sun, will primarily do. But heavier stars, which have a fair amount of nitrogen and oxygen and carbon in their core already, can go through another cycle, much more complicated, called the CNO cycle, or the CNO bicycle, and the carbon, nitrogen, and oxygen are all recycled, and what ends up happening net at the end is that 4 hydrogens are converted into 1 helium. So it has the same basic output. So this is a great graph. In fact, I first encountered this graph when I was taking a nuclear physics class, as an undergraduate, and I told the authors of our book, I said, this is a great diagram. This will really clear up for students why stars do what they do. So I think you should really include it in our textbook, and they did. So what does this show? Well, this shows the binding energy per nucleon in the nucleus of an atom for all the different atoms, from hydrogen, which is 1, all the way up to uranium, which is 92 protons. So going from hydrogen down to helium, that is a huge jump. In other words, that is extremely powerful fuel. And stars, therefore, can get away with burning it extremely frugally. They don't have to burn hydrogen very fast in order to accomplish their mission of holding themselves up against gravity. And also, since they're born mostly made of hydrogen, both of those things combine together to mean that stars burn hydrogen for almost their whole lives. And that's why when you look at just a sample of stars out there in the galaxy, you'll find that nearly all of them are burning hydrogen in their core, and that fundamental likeness of all these stars means that they all fall in a one-dimensional track across this temperature luminosity diagram that we call the HR diagram. That one-dimensional sequence we talked about is called the main sequence. Okay, so that's the first thing that stars do. But now see what the next 3 elements mean. So here's lithium, and here's beryllium, and here's boron, and they all have lower binding energies per nucleon. In other words, these are less tightly bound than helium. And it's another way of showing that ordinary nuclear fusion is not going to make these elements. This is not energetically favorable. So how is lithium, beryllium, and boron made? Well, the way they're primarily made is, well, out in interstellar space, the primary way in which they're made is heavier atoms get hit by cosmic rays, very powerful particles that are really the pieces of supernovae that have blown up and then been accelerated by the magnetic field in the galaxy. They're hit so violently that they basically get chewed apart, and the pieces can be lithium, beryllium, and boron. So that's where that comes from. Okay, but what stars can do is they can burn 3 of these heliums to make carbon. Okay, so 3 heliums make 1 carbon. And that's energetically favorable. That's going down on this diagram. That will release energy. It's endothermic. A star can hold itself up by doing that reaction, and that's what it does. Stars which do that are called red giants. Okay, now going to nitrogens, again, energetically unfavorable. So what ends up happening is the helium will combine, well, the carbon will combine with another helium, and that'll make oxygen, and there's oxygen. And then a beta decay will turn that into nitrogen. And I tell you what, all this nuclear physics can get really complicated and hard to remember, and I don't demand that you know that, because that's too much. We only have an hour and a half to try and get through this, so I'm going to just move forward. I'll just say that what stars can do is through alpha absorption, helium absorption, and beta decays, they can move up the nuclear fusion procedure here, and depending on how much mass you have and therefore how much temperature you can generate in your core, you can burn hydrogen to helium, helium to carbon, and to oxygen, and neon, argon, sulfur, magnesium, so forth, eventually to silicon. If you're a medium mass star, though, that's as far as you're going to get. So you cannot get to iron. I want you to notice where iron is on this diagram. It is at the very bottom. It's not the last nucleus, but it is the most tightly bound of all nuclei. So you should probably remember that. Iron is the most tightly bound of all nuclei. It's sort of the turnip of the periodic table. You can't squeeze blood out of a turnip, and you can't squeeze energy out of iron. So when a star ends up with an iron core, it's in big trouble, because it cannot do nuclear fusion to hold itself up. Only high-mass stars get to that point. Their evolution is going to be very different at that point. For medium-mass stars like the Sun, though, they will get to a point where they can't get the temperature any hotter to do these later stages of nuclear burning to generate these heavier, but still lighter than iron, chemical elements. And instead what they'll do is their nuclei, the cores rather, of the star, will get so dense, several tons per cubic inch, that the electrons are packed so tight that they refuse to get packed any tighter. Remember, electrons will repel each other. And really, it's more of a quantum effect, really. The Pauli exclusion principle comes in, and there's no more electron states in the dense core to be occupied, and so the star is held up not by ordinary gas pressure anymore. The core is not held up by gas pressure. It's held up only by what's called electron degeneracy pressure. And now the outer layers will come back in, some of them. Some will get blown back out. So these later stages of nuclear burning happen much more rapidly because the energetics, here, let's point out again. So hydrogen burning to helium, super powerful. Helium to carbon, still not bad. Carbon to oxygen, not as much. Carbon then to neon, not so great. And you can just see this line shallows out, and that means the quality, the energetic quality of your fuel is getting worse and worse. So it's kind of like going from the dragster fuel to the high octane to the low lead to the sawdust and then the wet sawdust, and the quality of the fuel gets to a point where finally you're trying to burn rocks like iron. So that doesn't work. Okay, helium burning star. So helium burns in the core, hydrogen burning in the shell, and while that's happening, the star is going to go through that phase more rapidly because it gets less energy out of helium burning, and it therefore will evolve quickly. The helium burning is still a powerful fuel, and because the inner core rather has gotten so much more dense, the luminosity, the energy output of the core, is actually going up, and going up fairly rapidly. And so stars spend almost so here's what the sun will do. The sun will spend almost its whole life right here. It'll slowly migrate up, very slowly. Here, I guess we start here at the zero-age main sequence. Very, very slowly, billions and billions and billions of years going by, and then it starts happening a lot quicker, going up here to the red giant area. So when the sun becomes a red giant, it's going to bloat out. It will swallow up the orbit of Mercury and Venus and almost the Earth. Now, it's not that the sun has gotten more massive. It's, in fact, gotten less massive. It's just kind of a cool little local thing. So I happen to be the discoverer of what was the most intensely spotted star ever seen. And that's HD 12545. And it had a star spot on it that covered half the star. And it kind of blew a lot of astronomers away. But other observatories got on it after I made the initial announcement and the discovery using equipment right here at Cabrillo College. and confirmed it, and so star spots can be surprisingly large. Anyway, this is a red giant, subgiant really, and just a little point of interest. Okay, I'm going to skip that. Okay, so what happens down here is there's kind of two stages to this, you see. So the core collapses. It makes the outer envelope expand because what you're doing is you're releasing gravitational energy. Finally, the core gets so dense that it actually ignites what we call the helium flash. And a lot of the helium, or a reasonable amount of the helium, all goes up at once, fuses to carbon. So much so that it actually expands the core so much that it shuts off the nuclear burning. And then the star actually migrates back down in luminosity till gravity takes over again, it climbs back up. So now we have helium burning in the core, and then we've got shell burning of hydrogen. And if you have an even, well, this is the evolution of the sun. So for the sun, that's the end. Now, what will happen at the very end is the last stages of burning tend to be a bit unstable, and the outer envelope is so big and so gravitationally poorly attached that it's pretty easy to just lift it off. And so what happens is it does lift off. That bloated red giant shell lifts off, and revealing now down at the center a tiny little object called a white dwarf, a newly dead star which is the core of this ancient red giant. The star's dead, but it still glows. Just like when you die, you'll stay warm for, I don't know, maybe an hour. But these guys are extremely dense, and they have very tiny surface areas, are only the size of the Earth, and so they cool off extremely slowly. They will continue to glow for billions of years, not just an hour. Now, when you first see the white dwarf, it's going to be way over here, extremely hot. It's going to cool fairly quickly because now it's exposed to the cold of outer space. And it's going to drift down here like this and end up in what we call the trash bin of the HR diagram, where the white dwarfs are. We'll see that a little bit better maybe in a later slide. Okay, I'm going to let you read that on your own. Again, this is a purple slide. Remember, purple slides are kind of a little extra beyond the usual. Not holding you responsible for that. But that is a nice diagram showing that what the star does is it kind of develops like an onion. And you end up with these cores. So here's carbon to oxygen fusion, and then helium to carbon burning, and then a helium layer, and then hydrogen burning still going on in the shell. So there's inert layers, and there's burning layers, and there's more inert layers. And the star is kind of growing from the inside out like an onion as these new chemical fusions are enabled by higher and higher temperatures and densities. I'm not going to talk about the S, R, and P process here. You can read about those on your own. It's a lot of complicated nuclear physics, but basically neutron capture and then beta decays because those are energetically favorable to make a more stable nucleus, and you kind of wander your way up and over till finally you find your way to a chemical element that is stable against any kind of radioactive decay, and then you just sit there. So look at the evolutionary timescales for something like the Sun. It's a main sequence star for 11 billion years. It's a red giant for only 1/10 of that. It's an asymptotic giant branch star for only 1/10 of 1/10. So only 100 million years. An asymptotic giant branch star for only 20 million years. And it goes through these thermal pulse phases. Well, the Sun's only going to go through one, but for less than 500,000 years. Planetary nebula is only lasting about 10,000 years. This is one reason why planetary nebulae, they're called planetary nebulae, because these little ghostly shells that surround stars are small and greenish initially, and they look kind of like the planets Uranus and Neptune. There's only a few hundred of them known in the galaxy, and it's because the amount of time that this shell is bright enough to be visible is very short. Compared to the 11 billion year age of the galaxy and stars like this, we're talking about only 10,000 years, so a millionth of the age of a star. And then look at the mass. Look at the mass of a solar type star when it finally dies. Half the mass is gone. Where did it go? Well, it got blown off during the time it was mostly a red giant, and then even more so with these later phases. Even now, the sun, though, has a solar wind, so it is gently losing mass. But the more bloated it gets, then the stronger the stellar wind and the faster it'll lose mass. So there's the evolution of the sun. Notice the time scale down here. Here's 12 billion years. Let's do that again. From here to here, 12 billion years. From here to here, only 300 million years. And then from here to here is only, I don't know, it's hard to figure. What is that? A thousandth of a billion years? So, 1 million years, something like that. So obviously stars go through big changes only at the very end of their life. And we're all doomed. Okay, but you already knew that, so let's go on. I don't think I'm going to click on the web simulator. I'm going to let you do that. You can play around with it and watch how fast stars evolve on the main sequence. I do want to talk briefly about carbon stars because they're pretty cool. If you think about the helium burning to make carbon, then you may ask, well, okay, but then we're made of carbon, and the Earth has carbon, and plants are made of carbon. How'd that carbon get here if what you're telling me is the white dwarf sounds like it's mostly made of carbon at the end, and it's not going to get out. It's going to just sit there. It's going to, be part of this stellar corpse. Yeah, that's true. So most of the carbon that gets made never gets out. If it doesn't get out, it's not going to be any good for creating life forms like you and me. So we have to be very grateful for a certain kind of star called carbon stars. Carbon stars are red giants which have very deep convection zones. Their convective instability zones extend all the way down into the core where the carbon is made. And so they are actually able to dredge freshly made carbon that they've generated all the way to the surface, where stellar winds then carry it away from the star. It cools, and then the carbon combines with carbon and makes little graphite grains. Okay, so graphite grains and also carbon monoxide. It's another thing that's made. Carbon and oxygen are right next to each other in the nuclear burning sequence, so you get a fair amount of carbon and oxygen typically in all this. So these graphite grains are the most common form of interstellar dust. And they're kind of like the Pigpen character in the Peanuts cartoon. They shroud themselves in their own dust, reddening the star dramatically. So carbon stars are kind of cool. If you get a chance, again, to take one of my field astronomy classes, then I'd urge you to go. I always try and find a carbon star to look at because they're so pretty. They're a deep red, ruby red color, and they're the reddest of stars out there, and it's because they're not only cool and therefore red from thermal radiation, but they're enhanced reddened because they're having to shine out through their own dust. So there's a carbon star, photograph from the 2-mass survey. Notice how red that is compared to ordinary white dwarf. Not a white dwarf, ordinary white main sequence star. So maybe you should remember, actually. Where are we? Here we are. The Cepheids, classical Cepheids. They're named after the prototype star Delta Cephei. These are pulsating stars that are extremely useful because their period of pulsation is tightly correlated to their luminosity. So they become great standard candles, and they're also way up here at the top of the HR diagram. They're among the brightest of all stars, and therefore you can actually literally see the individual Cepheids in nearby galaxies. They stand out from the crowd. Okay, so here we talk about white dwarfs again. Stars collapse until they can't get any tighter. They're only about the size of the Earth. And now it is so-called electron degeneracy pressure that is holding up the white dwarf. So how does that work? Well, it's probably too tempting for me to try and describe it as just the electrons repel each other and refuse to get packed any tighter. It's really more accurate to think of the core now as being so dense, it's really acting like a single gigantic atom. And we already encountered ordinary atoms in the periodic table, and the electrons are only allowed to be in certain quantum levels, the first orbit, the second orbit, the third orbit. And there's a principle that nature has decided to invoke called the Pauli exclusion principle, and that says that you just won't find any two electrons in the same quantum state. You can fit two electrons per orbit, but one has got to have so-called spin up and the other one's got to have spin down. So electrons do have a little bit of a magnetic moment, and they can be thought of as like they're spinning. So you can pack two electrons per orbit. But if the entire star, the entire remnant of the star, can be thought of as one gigantic atom, there's also quantum levels for that atom, about as many now, in this case, as there are electrons. And so when every quantum state is full, there's no way for the electrons to go into a lower orbital. They are already occupying the lowest of all the orbitals in that gigantic quantum object called the white dwarf. So that pressure will hold up the star, and it's not a gas pressure, and therefore the white dwarf will not get smaller as it gets cooler. It'll just stay the same size. So it just sits there and it cools. It can't collapse further because it's held up by electron degeneracy pressure. It can't generate any more energy from nuclear fusion because it can't get hot enough. It can't tap gravitational potential energy. So all it does is it just sits there. Again, we name them because they looked to the early astronomers kind of like the planets Uranus and Neptune. They're greenish. They're greenish because of an emission line of doubly ionized oxygen. But they have nothing whatsoever to actually do with planets. So the planetary nebula phase happens up here as the star has gotten so bloated the outer envelope is now blowing off altogether, and it's revealing the new white dwarf in the center. Okay, so there we go with that. There is the Eskimo Nebula. Looks a little like a planet if you look at it with an old telescope, smaller telescope. And it's glowing. This gas has been blown off from the new white dwarf. There's the new white dwarf, the little blue star, not the red one, brighter. This red star is unrelated. It's a little blue star in the middle. That's the new white dwarf. Another one. Hubble Space Telescope shows details of these shells that are blown off much better. The Helix Nebula. And okay, there's one of the brighter ones. This is the Ring Nebula. Brand new white dwarf in the middle. Another white dwarf. There's some galaxies in this picture too, which are in the way, way distant background. 10, 20, 100 million miles away. Whereas this planetary nebula is only about maybe 50 light years away. The Spirograph Nebula, the Eskimo Nebula, Eskimo Nebula again. Doesn't look quite so friendly and Eskimo-like when you've got higher resolution. Looks kind of like an alien. So old white dwarfs, they just slowly cool, but as they cool, then it becomes possible for the carbon to actually crystallize. And of course, crystallized carbon is diamond. So we actually do see gigantic diamonds forming out there in the sky. We can see from the vibrations of some white dwarfs, it's telling us that they're transforming into crystalline carbon. Okay, now what happens if we're in a close binary system? Well, then you've got a lot more adventure ahead. So now we've got two stars, and we start out with one star here, one star here. This star is going to be the more massive one, and the more massive one goes through its evolution quicker. We're picking it up here at a later stage. It has already gone through its red giant phase. It has transferred mass. It is bloated out and transferred mass onto this star. And then this star finally goes to being a white dwarf. Now it's this star that goes through its red giant phase, but again, there's not enough room to fully become a red giant, so it begins transferring its matter back onto this star. But now this star isn't a regular star anymore. Now it's a very tiny white dwarf. And now the matter is falling down a deep, steep gravitational well. A lot of energy gets delivered. And it falls onto the white dwarf, and it builds up a layer. Now, that layer is sitting on a star, a white dwarf, which is mostly made of carbon. And that carbon, you know, had to be at least 180 million degrees, because that's the temperature that helium fuses to make carbon. However, it's not that temperature on the surface because it was exposed to outer space for a while and cooled off. The stuff that is falling in from this star is hydrogen, mostly hydrogen. Why is it mostly hydrogen? Whoops, I don't know if you guys are seeing that or not. There's an asteroid occultation coming up. I'm going to get rid of that. Be interesting to see why that shows up in my show. Anyway, back to here. So this red giant is going to bloat out and then begin transferring matter onto the surface of the white dwarf. Because the white dwarf beneath the layer is so hot, that layer might eventually ignite, getting up to 10 million degrees. Now, though, instead of being like gasoline inside of the cylinder of a normal engine block, burning very, very slowly and regularly, now it's like gasoline we poured on the outside of the car, and we just put a match to it by making it hot enough to fuse hydrogen to helium. And unconstrained, all that hydrogen will fuse. So a nova happens when a white dwarf collects enough matter from its red giant companion, getting dumped onto it, onto this accretion disk that then settles onto the white dwarf, and the white dwarf eventually heats up that layer hot enough to go through nuclear fusion, and the hydrogen burns to helium all in a flash. Okay, so this is a nova. That's Nova Persei on the right side. But there's something worse that can happen. Suppose the white dwarf is an old white dwarf. It went through its evolution quickly because it was more massive. And suppose that white dwarf is at about 1.3 or 1.35, something like that, solar masses. Now there is a limit to how massive you can make a white dwarf. If you make it more massive than 1.4 solar masses, that star will now collapse. The gravity is so strong it can actually overcome the Pauli exclusion principle, and it is now energetically favorable for the electrons to combine with the protons and make neutrons. When that process begins, the core begins to collapse. As the core begins to collapse, the carbon that's there is now becoming hot enough that it can fuse. And because it is held up by electron degeneracy pressure and not by gas pressure, as the carbon begins to fuse, that added energy is not going to expand the star and quench the reaction. Instead, it's going to get to a point where basically all the carbon blows up at once. That is not a nova, that is a supernova. It's a so-called carbon bomb supernova, is the way our textbook describes it. It's also called a type 1a supernova. And it's what happens when a white dwarf close to the 1.4 solar mass upper limit that electron degeneracy can support gets more mass and pushes it past that limit. The star collapses and then blows up. Type 1a supernovae are the most sought after objects by cosmology astronomers. And the reason is because they're all the same. They're all virtually the same. They're all 1.4 solar mass white dwarfs passing through this so-called Chandrasekhar limit, collapsing, triggering nuclear carbon fusion, and they all blow up at once. Their maximum luminosity is all the same. They're all at an absolute magnitude of negative 19.4. Now, it's not totally true that they're all literally identical because they can have slightly different chemical compositions. However, we've known for a long time now that there's a strong correlation between the chemical composition that we see in these supernova remnants and the rate at which the supernova declines in its brightness. So that's what you see up on top in this diagram. You see different chemical composition type 1 supernovae will decay at different rates. So the more massive ones will decay at a slower rate, and the less massive, the not mass, but the chemical compositions, and I forget at the moment whether these are the high metallicity ones or the low metallicity ones. But anyway, the giveaway is the rate of decline. So if astronomers can find these and measure their rate of decline, then they can calibrate them all and put them all onto a common light curve. So these are great standard candles, and they are the brightest things out there. They are the most luminous things except for galaxies themselves. And that means that we can see them all the way out to the edge of the observable universe. And it is by means of type 1a supernovae seen at all distances in the observable universe that we are able to measure not only the expansion of the universe, but the rate at which that expansion has been changing over the history of the universe. So without type 1a supernovae, we'd know a lot less cosmology than we do. Okay, what about high mass stars? So they have short lives, short and violent lives. They're the ones that can heat their cores all the way to the point of fusing up to and including iron. Since iron is the most tightly bound of all nuclei, the star is now in a big problem. Nothing can hold it up. You cannot get energy to hold you up further when you have an iron core. So here's what a 5 solar mass star will do. Starts here, hydrogen to helium burning, helium to carbon burning, comes up and goes back and forth here as it goes through more different kinds of burnings. A 10 solar mass star is going to do hydrogen to helium, helium to carbon, come up here, wander around, and then at some point it's going to go bloop and blow up. It is going to leave the HR diagram because it leaves, well, it leaves, it blows up. The star is gone. It becomes a supernova. In the process of getting there, it's going to, again, grow like an onion, like we talked about. The highest mass chemical elements, the iron, is in the center, and then silicon. 2 silicons make an iron. You got magnesium and neon and so forth. You don't need to remember all these different chemicals. I do want you to remember iron is the most stable of all nuclei. I think that is important. There's that diagram again. So what about a 20 solar mass star. What is its life like? Well, now the hydrogen fusion doesn't take 10 billion years. It takes only 10 million years, 1/1000th as long. The helium fusion takes only 1,000,000 years. The carbon fusion only 300 years. The neon fusion lasts only 6 months. And silicon burning into iron only 3 days. Now here's a star about to go supernova. It's called Eta Carina. It's the most massive star that we know of, at least it was the last I checked. It's about 150 to 200 solar masses. Huge stellar winds are causing these nebulae surrounding it. Looking at it more closely, strong stellar wind. So now what happens at the end? Well, the iron core at the center gets larger and larger as more and more of the silicon burns to make iron. Again, eventually, because the iron cannot support itself by nuclear fusion, the weight is going to become so heavy that you energetically favor this sort of backwards weak force interaction where the protons will combine with the electrons and make a neutron. The normal thing is if you take a neutron and pull it out of an atom and leave it all by itself, they kind of go a little crazy. All by themselves, they can't handle it. And the neutron will literally just fly apart and become a proton and an electron and a neutrino. But here, we have it the very opposite of being all alone. It's now so crammed together with other stuff on top of it, it goes the opposite direction, combines and makes a neutron and a neutrino. We talked about neutrinos with the sun, these little teeny ghostly particles. They have no charge, so they don't interact electromagnetically. They are not baryons, so they don't interact by the strong force. They only feel the weak force and gravity, and because of that, they travel through almost everything with no trouble. However, the density in the centers of these stars is so high that even the neutrinos have a hard time getting out. So what happens is in just 0.2 of a second, the nuclear burning causes the core collapse, which raises the density and accelerates the reactions until the neutrinos are so densely confined that they help to blow apart the star. Now, all the details of supernovae type 2, which is what we're talking about now, are not really fully worked out because it's a very non-equilibrium process and takes big computers with lots and lots of physics, and it's just really hard. So, but we have some of the world's experts in doing that. Stan Woosley and his group up at UCSC and the people he's trained are some of the best people in the world for leading the understanding of these objects. So there you go. We've got a supernova type 2. Here's some interesting factoids. 99% of the energy release, the gravitational potential energy of the star, the collapse goes into neutrinos. 99% goes into neutrinos. Only 1% of that energy goes into the explosion. Again, the neutrinos mostly escape, but it's so dense that as much as 1%, which is actually a pretty vast amount for these things, will go into the explosion. Only 1/100th of that 1% goes into the visible light. And yet still, the light is bright enough to equal the entire galaxy. 100,000 million stars altogether will not outshine the brilliance of that supernova. And that will last for weeks or even a month or two, outshining the entire galaxy it lives in. There's a hell of a lot of neutrinos, and neutrons flying around in this process. So protons and electrons combine to make neutrons. And those neutrons glom onto other elements, and they make heavy isotope versions of the elements that are heavier than iron, so-called R process elements. So R means rapid. You build up a whole lot of neutron-rich nuclei. And then through the weak force, then many of those will decay and become slightly less neutron enriched, but different chemical elements. too much nuclear physics. I don't want to burden you with all that. But here's another interesting fact, probably worth remembering, and that is that we have found through more detailed modeling that gold and platinum, the platinum elements, are made primarily not in supernovae explosions so much as in the combination of neutron stars, collisions of neutron stars. So how would you get that? Well, if you had two high-mass stars, each go supernova in a tight binary system, and somehow be so tight that they don't unbind by losing enough matter to fly apart, but they stay bound together now as two remnants, two neutron stars. Those neutron stars will spiral together and eventually combine in another kind of explosion, and out of that comes gold. So that's one reason why gold is so rare. You need a pretty unusual situation to favor the formation of gold. Okay, let's look at some supernova remnants. There's Cas A. This is the supernova that blew up in 1680, the last one that we know of that blew up in our galaxy. We're long overdue for these. Typically they go off about once a century. We've now gone 4 centuries without one. Now that's in a neighboring galaxy, or no, this is in our galaxy. This is Kepler's supernova. So this went off in 1604. This one's in a neighboring galaxy, the Large Magellanic Cloud. And so is this one. This one's in our galaxy, the Spaghetti Nebula. And the Veil Nebula is one of the nicer objects in the sky for astrophotography. My astrophotography students love to photograph this one. Part of the Veil Nebula. Very beautiful. Another part happens to be very close to a bright star, naked eye star in Cygnus. And then this is the Crab Nebula. So this is a supernova that went off 1,000 years ago and was recorded by the Anasazi Indians and also by, of course, the Europeans. And at the very center, that object right there, that is not a white dwarf. That is a neutron star. So this is even more extreme than white dwarfs. This is a star of pure neutrons. That's what's made at the center of the collapse of these high-mass stars. And it's only about the size of a city, about 10 miles across. Now, as pure neutrons, it's way more dense even than the white dwarf, which is made of tightly bound chemical elements, so mostly carbon. But this has even had the electron space moved out. This is nothing but neutrons. And so rather than several tons per cubic inch, this is several billion tons per cubic inch. So imagine an entire large mountain compressed down into, a thimble. That's the kind of mass we're talking about. Cutaway of a neutron star. It's all neutrons. So they have the mass of the sun, yet they're only about the size of a city. Pretty amazing. They warp space pretty severely. The gravity is so strong, these things are almost black holes, but not quite. So a photon of light could easily lose a large fraction of its total energy just escaping the neutron star, maybe 10-15% of its energy. And so there's a strong gravitational redshift to that light. Okay, now, so these things are rotating. Stars, when they're normal, are rotating. High-mass stars might rotate once every 10 days or so. Now, what's going to happen, imagine a figure skater, when she brings her arms in, she spins faster. Well, now we've taken a star that was normally about 1 million miles across, and now it's only 10 miles across. So we've compressed it by a factor of 100,000. So the rotation speed is going to go up by a huge amount, and so these things are now spinning at several to hundreds of times per second. Now that rapid spin of something this hot and still having charge in it, the neutrons have a magnetic moment to them even though they don't have a net charge, but they have a magnetic moment that they feel and can align themselves with and produce a magnetic field. They have actually a very strong magnetic field. And the magnetic field causes lines of magnetic force to go out along the north and south poles, and they act as out points for electrons that are out here spiraling in. They get in closer and closer, and then they actually get flung back out along the magnetic axis, as does light. So light itself will actually be channeled along these magnetic field lines because the electrons spiraling in will emit a certain kind of radiation called synchrotron radiation that is aligned with the magnetic field lines. And so the way to think of these things is they're like gigantic lighthouse beams. And those beams are aimed in a particular direction. And when those beams go across the direction to you here on Earth, then we see a flash of light. So if these things are spinning around at several times per second, then what you actually see is a flashing light that's flashing many times per second. And when we first discovered these back in 1968, they were labeled LGM1 and LGM2, and LGM stood for Little Green Men. It was a bit of a joke. They didn't really think they were extraterrestrial, but it was spooky how incredibly precise were the timings of these objects. So they're very, very, very good clocks. Okay, so we talked about that. There's a pulsar. Oh, so these objects that are flashing light, we call them pulsars. So here's a pulsar in the center of a globular cluster. So there it is there when it's bright, aimed at us, and here when it's not so bright. Now, how do we detect the neutrinos? So we've put together this great theory of how high mass stars collapse and generate neutron stars, but is there evidence to really support it? And the most direct evidence that really confirmed that this was right was the actual detection of the burst of neutrinos given birth to by the nearest supernova to have gone off, as far as we know, in the last 400 years. It was in a galaxy about 3 Milky Way diameters away from us called the Large Magellanic Cloud. And we had a neutrino detector at the bottom of the Homestake gold mine operating. And let's see, was it that one or was it... I think it was the water detector, actually, in Canada. And it detected the neutrinos, which ran into some of the electrons inside the water in that Sudbury detector and caused those electrons to accelerate up to near the speed of light and emit a bow shock of light. Characteristic Cherenkov radiation, little circle of light, and the circle of light tells you where they came from, and where they come from. They came at the time and from the direction of that supernova, which was detected that very night. So that's Cherenkov radiation, something I'm not really going to ask you to understand, but basically it's when you take a charged particle and you accelerate it up to past the speed of light in that medium. Now, you might think, wait a minute, Rick, nothing can go faster than light. Nothing can go faster than light in a vacuum, yes. But you can go faster than the speed of light in that medium. And then you emit a shock wave, a bow shock. And that kind of light is called Cherenkov radiation. I'm going to skip that. So there's supernova 1987A. This was the star that blew up in the Large Magellanic Cloud. And we saw the neutrinos. We detected the neutrinos from that explosion. They arrived hours before the light did, but then that too made perfect sense. The photons, after all, had to spend a few extra hours fighting their way out of the hot ionized cloud that was the surrounding star that they were blowing up. And so they had delayed a little while before they were finally freed, and then could travel, of course, at the speed of light to get to us. The neutrinos have a tiny bit of mass, and they actually travel slower than the speed of light, very, 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 very slightly. But because they didn't have to work their way out through that layer of surrounding star, because they are only feeling the weak force, they actually got a head start and beat the light to us by a few hours. So there's the neutrino observatory at the bottom of the Sudbury mine, and these are all these little dots, these little things on top here are the other ends of photomultiplier tubes that are really aimed inwards inside this giant globe of water. It is giant. See this person here? That's a person. Give you some scale. There's another person. And it proved that indeed neutrinos are emitted, and therefore a neutron star is born at the centers of the stars. Let's look at the cosmic abundance of the elements. Well, we talked about this, how gold is created. More nuclear physics than you need to know. Forget about that. Our process, a little bit too much detail. This should be a purple slide. But I did want to show this. I think it's pretty interesting. Hydrogen and helium are very common. But then these are the two elements that emerged from the Big Bang, as we'll learn later. Lithium, beryllium, and boron, extremely rare. They're like as rare as gold and silver. You might not think so, and you might say, well, gee, lithium's not that valuable. Heck, I throw out lithium-ion batteries all the time. Yeah, well, it's because the Earth is, because lithium is so lightweight, it tends to collect at the surface of the Earth, and salt processes concentrate it further into dry lake beds. And so nature has managed to take this cosmically very rare element and concentrate it for us so that it's pretty easy to find. And so yeah, it's not all that valuable. Same with beryllium and boron. Okay, and then much more common again, carbon, oxygen, neon, nitrogen. These are elements that are made early in the sequence, so lower mass, more common stars, but still medium mass stars and high mass stars will make these, and they'll be in the outer envelopes of these onion stars, and they'll tend to get blown out. So yeah, there's a lot of those. But then these elements are much more rare, and then, whoa, this turns around. What's this hump doing here, centered on iron? Well, it's because when a star develops an iron core, it blows up. And a lot of that iron, now we talked about some of the iron making a neutron star in the center, but a lot of that iron just gets blown out. And isotopes of that iron can turn into nearby elements, so manganese and nickel, for example, cobalt. And then these elements are much rarer, so these are only created in our process, the rapid process of the supernova explosion itself, or in neutron star collisions, which of course are very rare. Gold, silver, platinum, uranium, etc. Another picture, same thing. And then I mentioned cosmic rays. So what these are bits of supernova explosions. They get accelerated by processes in the magnetic field of the galaxy. They're already moving very fast, many tens of thousands of kilometers a second from the supernova itself, but then they can get accelerated further by bouncing around in the magnetic field of the galaxy, so that when they finally arrive at us, they could be essentially moving at the speed of light. And they bang into the upper atmosphere, and they have so much energy they create all kinds of unstable baryons like pions and kaons and lambdas and all kinds of stuff, some of which make it to the ground. I'm going to skip that since we are getting an hour and 10 minutes into our lecture. We only have an hour 30. So these are the possible end states of a star, depending on the mass. If your mass is less than 1.4 solar masses, then you can be stable as a white dwarf. If your remnant mass is more than 1.4, then you can't be a white dwarf, and you could be stable up to 2 solar masses as a neutron star. You can find neutron stars that are less massive than 1.4, but then that's because they were created in stars that were much more massive than that and then blew up, and a lot of the outer layers got knocked away. And then the theoretical limit is 2 solar masses. So if you go beyond 2 solar masses, there's nothing that can hold you up. You bend space around yourself so severely that the radius of curvature of space itself is sharper than is the radius of curvature of your surface. And you essentially collapse in on yourself. There are no pathways out from that. You become a black hole. So for a black hole, the gravitational redshift would be 100%. All the energy of the photon is eaten up in its attempt to escape. In other words, none of it gets out. So if you had a very strong black hole very, very nearby, and you had it in a rich star field, then it might distort the star field like this. So what you're seeing is that the black hole's in the middle here, and no light gets to you from that direction because that would have to be light from inside the event horizon, and it can't get out. The light that you see concentrated along the boundary is really the light of background stars that are back, actually, they are back here behind the black hole. And that light was heading off in this direction, and then when it passed near the black hole, it got bent by the curvature of space from the intense gravity, and it got bent into your line of sight, so that now you see the concentrated starlight of really all the stars that are inside here now put onto the surface, okay, of the two-dimensional star field that was back here is now concentrated into a one-dimensional field called the event horizon of the black hole. When we talk about the event horizon, is the escape velocity at that point is the speed of light, or was right at the speed of light, and inside it's greater than the speed of light, and so nothing can get out. I'm not sure why this diagram is here. I'm going to skip it. Now, it was in one of my Astro 4 classes. I know we already showed this cartoon. If it was our day class and not our night class, I apologize for going over this again, but then this will be good because now we have it recorded. I'll even try to post this on YouTube, and so this maybe will be useful. Anyway, cartoon dating back to the 2008 recession. There'll probably be also funny ones about the current recession, the coronavirus recession that we're starting right now. Okay. So, let's look at how stars evolve in a star cluster going forwards in time. So what happens is the high mass stars that are up here will evolve through their whole lifetime very quickly, as we talked about. So these guys are already evolving off the main sequence, even though this star cluster is still very young. The highest mass stars might only last for a few million years on the main sequence. These stars are all main sequence stars. They're burning hydrogen to helium in their core. But then what about these guys? Well, these guys are so low mass, they're little red dwarfs, that they haven't even gotten down to the stability point and become main sequence burning stars. They're poking along, slowly pulling themselves together under their weak gravity, and they aren't yet really fully stars. They're in the variable star stage called the T-Tauri stage of evolution. So now this is pretty cool. We can age date a star cluster. That's something you cannot do with an individual star sitting out there all by itself. Stars kind of age like we all would like to do. We'd like to come of age, be full flower, be beautiful for our entire lives, and then not age at all on our surface until the very end, and then we just, we die and that's that. That's what stars do. They go through most of their life looking, fresh and lovely until just the last 10% of their age, and then they go through big changes. Then they pay for it all. Okay, so how do we age date a star cluster? Well, we understand stellar evolution, we believe, very well. We can, in a computer, age date a star and find when it runs out of hydrogen in the core, and that's when it will now evolve off the main sequence and go up and become a red giant. So it is this main sequence turnoff point. That's what tells you the age of a cluster. So for this very young cluster up here, NGC 2362, it's only 10 million years old. The turnoff point is way up here at a luminosity of almost 1 million times the luminosity of the sun. The Pleiades, bright naked eye cluster, it's about 60 million years old. M11 that we looked at the beginning of this show is about 150 million years old. The Hyades are almost 700 million years old, and M67 is 3 billion years old. Most open clusters, when they get to be that old, have already completely dissolved, but M67 is a particularly dense cluster, and it's actually still hanging around. Okay, so that's our stellar evolution talk. The next lecture that we will have will be on end states. We'll talk about black holes in a little more detail, and then begin to talk about the Milky Way galaxy. So we don't yet have any quizzes. So again, I'm making this during still the beginning points of turning this into an online course, something I've never done before. Generating and giving fair quizzes in an online format is not so easy, and I haven't really had time to flesh it out yet. So I will tell you by email when we're ready for our next quiz. Okay, gang. I will see you next time then.